Hello, and welcome to the fourth and final lecture in our series on electric power quality. My name is Ben Stevens. I'm a research assistant to Professor Surya Santoso at the University of Texas at Austin. This final lecture will cover the causes, effects, and characteristics of harmonics in power systems, as well as strategies for mitigating the problems associated with them. Harmonics are waveforms present in a power system that oscillate at frequencies that are integer multiples of the fundamental power system frequency. If the power system fundamental frequency is given by f1, harmonic frequencies will be equal to n times f1, where n is any positive integer. The presence of these harmonic waveforms in power systems, called harmonic distortion, is usually caused by loads with nonlinear voltage current characteristics. Linear loads draw current that is directly proportional in magnitude to the voltage applied across the load. Resistive loads are linear, drawing perfectly sinusoidal currents when sinusoidal voltages are applied across them. The voltage and current waveforms will also be perfectly in phase for a resistive load. Inductive loads are also linear in steady-state operation. The current drawn by an inductive load with sinusoidal applied voltage will also be a perfect sinusoid, although the current will lag the voltage waveform by 90 degrees. Nonlinear loads draw current waveforms that are not directly proportional to their applied voltage. When a sinusoidal voltage is applied to a nonlinear load, the current waveform drawn will not be a perfect sinusoid. The current drawn will be periodic, and therefore its waveform can be expressed as the sum of a series of sinusoids oscillating in integer multiples of the waveform's fundamental frequency. This expression of a periodic function as the sum of a series of sinusoids is known as a Fourier series. In general, any periodic function can be expressed in the form shown in the top right as a weighted sum of sines and cosines, each oscillating at a frequency that is an integer multiple of the fundamental, plus a constant value. The formulas used to determine these weights and the constant value are shown in the bottom right. The figure on the left shows how a distorted waveform can be decomposed into a sum of harmonic waveforms. Adding the values of each of the waveforms shown in the middle at each point in time will produce the waveform shown on the left. One example of a nonlinear load is a three-phase, six-pulse rectifier. The current waveform drawn on phase A is shown in the figure on the bottom left. It consists of a series of square wave pulses alternating with periods of zero current. This particular waveform has harmonic components with frequencies that are equal to 6k plus or minus 1 times the fundamental. In other words, the harmonics present include the 5th, 7th, 11th, 13th, 17th, 19th, and so on. The Fourier series for this current waveform is shown on the right. The figure in the top right shows another example of the current drawn by a nonlinear load, a switch-mode power supply. To the right, measurements of the phase angles and magnitudes relative to the fundamental of each harmonic are shown. Unlike the previous example, all odd-numbered harmonics are present in this current waveform, and the component's magnitude tends to decrease as its harmonic order increases. Even-ordered harmonics are essentially absent in this current waveform, as is usually the case in power systems. Distorted load current is ultimately caused by switching operations in power electronic converters. As this non-sinusoidal current is drawn through the power system, it interacts with the system impedance, causing non-sinusoidal voltage drops, ultimately leading to a distorted system voltage. Each harmonic component causes a voltage drop across the impedance as it travels through, and this voltage drop will have the same frequency as the harmonic component causing it. Thus, the voltage at the load bus will have harmonic components introduced that were not present at the source. Linear loads also cause voltage drops across the system impedance, but the current drawn by the loads is sinusoidal, at the same frequency as the system voltage. Therefore, the voltage at the load bus, while slightly lower in magnitude than that at the source, will not have any harmonic components introduced. If, however, the load is nonlinear, the current drawn through the system impedance will be non-sinusoidal. Each harmonic component of the current will cause its own voltage drop, making the resulting voltage at the load bus the sum of a series of sinusoids oscillating at integer multiples of the fundamental frequency. As discussed in previous slides, this represents a distorted voltage waveform. Notice that the system reactance increases for higher order harmonics because inductive reactance is proportional to frequency. The magnitude of voltage distortion caused by nonlinear loads depends on two factors: the upstream system impedance from the load and the magnitude of the harmonic currents drawn by the load. Large upstream impedances can cause significant voltage distortion even for relatively small harmonic currents, and of course larger harmonic currents will cause greater voltage distortion. While we speak of nonlinear loads causing distortion or drawing undesirable currents, we should note that this is not typically the result of negligence or malice on the part of the operator of the load, but merely the manner in which the load normally operates. IEEE Standard 519-1992 stipulates that both parties, the load end user and the utility, share responsibility in minimizing harmonic voltage distortion. The end user may not inject an unreasonable amount of harmonic current into the system. Meanwhile, the utility must ensure that system impedances are not so large as to induce voltage distortion as the result of reasonable levels of harmonic current. A low impedance power system is referred to as a strong system, as harmonic current injections will cause little distortion to voltages in such a system. Conversely, a high impedance power system is referred to as a weak system. Nonlinear loads can be modeled as current sources, each injecting harmonic currents into the power system. These currents flow toward the source, interacting with upstream system impedances. As shown in the figure on the right, the impedance of the system increases linearly with the frequency of the harmonic current. If the system impedance contains shunt capacitive reactance in addition to series inductive reactance, problems can arise due to resonance. In the power system shown on the right, the utility bus to which the harmonic current sources are connected is outfitted with a capacitor bank. The upstream source impedance and the capacitor bank together act as a parallel LC circuit from the perspective of the harmonic current sources. Instead of a linear relationship between system impedance and current frequency, the LC circuit has a characteristic frequency, at which there is a large spike in system impedance. Harmonic currents at or near this frequency will cause significant voltage drops, leading to distortion. Here is a model made in PS-CAD simulating an energizing operation of a shunt capacitor bank on a power system. The Thevenin equivalent of the upstream system is a 69 kV voltage source with an inductive reactance and 1 ohm series resistance. In this case, there is no harmonic current being injected into the system. At time 0.11 seconds, the circuit breaker to the 60 megavar capacitor bank is closed, energizing the bank. There is a transient response to the energizing event, which is damped out after 2 or 3 cycles due to the resistance. Now, the energizing operation is repeated, but with the presence of 80 amps of harmonic current oscillating at the 5th harmonic frequency. With this current present, the transient, instead of being damped out, evolves into a persistent resonant response, resulting in highly distorted voltage and current at the capacitor bank. The energizing operation is repeated once more, again with 80 amps of harmonic current injected into the system. This time, however, the current oscillates at the 25th harmonic frequency. The transient response to the capacitor bank energizing operation now closely resembles that in the first example, with no harmonic current present. These examples show the importance of identifying any resonant frequencies in a power system and ensuring that harmonic currents at or near these frequencies are not introduced into the system. Another type of resonance that can occur is called series resonance. This can occur when another customer load contains a service transformer supplying a capacitive element, such as a capacitor bank used for power factor correction purposes. This branch of the system appears to the harmonic current sources as a series LC circuit. Series LC circuits also have a resonant frequency, but at this frequency the inductive and capacitive reactances are equal and opposite. Thus, the impedance in this branch is purely resistive at this frequency, and thus very small. A power system containing such a downstream capacitive element will have the potential for both series and parallel resonance. The figure here shows the equivalent circuit of the system as seen from the harmonic current source. At one frequency, the current will experience parallel resonance, resulting in a large system impedance. At another frequency, the current will experience series resonance, resulting in a very small system impedance. The series resonant frequency will always be larger than the corresponding parallel resonant frequency. To understand how to mitigate the effects of harmonic currents, recall what we have learned about these currents. They are produced by nonlinear customer loads and flow into the system, distorting system voltages through interacting with the system impedances. Lower system impedances result in less voltage distortion, while large impedances cause larger distortions. Harmonic resonance occurs when the frequency of the harmonic current in the system coincides with one of the system's resonant frequencies. Harmonic resonance at a parallel resonant frequency results in heavy voltage distortion, while resonance at a series resonant frequency will result in very little distortion. There are therefore 3 causes of harmonic voltage distortion problems. First, the magnitude of injected harmonic currents may be too large. Second, the system impedance through which the harmonic currents flow may be too large. Finally, a harmonic current may be oscillating at a resonant frequency, causing that current to interact with a large system impedance. Large harmonic currents can be mitigated in several ways. The load itself can be altered, changing its operation or the manner in which it connects to the grid in order to reduce the harmonic currents that it produces. Additionally, loads can be connected in parallel to a filter, tuned to series resonance with the harmonic frequency in question. This creates a short circuit for currents at that frequency, keeping them from entering the larger power system. Parallel resonance in the system can be avoided by altering the capacitor bank, changing either its size or position in the power system. Either of these alterations will change the system's resonant frequency. If parallel resonance cannot be avoided, the capacitor bank may have to be removed entirely. Harmonic control should be implemented as close as possible to the source of the harmonic currents, that is, on distribution feeders. Capacitor banks on utility feeders can cause harmonic resonance, in which case they should be resized or moved. Certain harmonics, called triplen harmonics, can be blocked by installing delta-connected transformers in place of grounded Y connections, or by adding a reactor to the Y transformer's neutral connection. Finally, filters can be added at the far end of distribution feeders to draw problematic harmonic currents away from the upstream power system.